Welcome back to the third and final video for Thursday, February 25th. In this video, we're going to talk through the lab instructions for lab number 5. Lab 5 is about the tensile testing of metal specimens and wood specimens. And the reason why we do these two specimens, these kinds of specimens in lab 5, is for a couple of reasons. Number one, it's good to split them up. We do plastic specimens in lab 4, and that gets you some experience using the Instron machine. So it's good to get some practice and split them up because it would take a long time to do all of the plastic, wood, and metal specimens in one lab. That would take a long time. We probably couldn't get everyone through on the same day. But the other, probably more important reason, honestly, is why we do the plastic specimens for lab 4 and the wood and metal specimens for lab 5 is because, if you notice, these are both round specimens, and this is a flat specimen. It's flat on both sides. So that affects the test fixture that we have to use to do the tensile testing on these. You may or may not have noticed, but the jaws that were gripping these plastic specimens in lab 4 were flat. They were flat jaws that gripped straight onto this flat plastic dog bone. But we actually have to use different grips. They look kind of similar, but they're just rounded instead of flat. So we have to use those rounded grips that will grab onto these rounded specimens. They're about the same diameter, and so we can use the same jaws for both of these. These metal specimens are actually made down in our machine shop, in our machine lab down there. It's made on the CNC lathe. So this is a aluminum specimen, the 6061, but we also make the 1018 and the 1045 or whatever other metal specimens we want to make on the CNC lathe down there. So we make new ones every semester so that we can destroy more of them every semester. So let's go ahead and flip over to the lab manual, and you can follow along on page 47 of the lab manual. All right, here is lab 5, starting on page 47. So the materials that we're going to use 3 different kinds of metal, aluminum 6061, and then 2 different kinds of steel, 1018 steel and 1045 steel. After listening to today's videos, you should be able to tell me the difference in carbon content between this specimen and this specimen. So you should also be able to tell me which of these 2 specimens you think is going to be stronger and which of these 2 specimens you think is going to be more ductile. All right, those are some of the concepts that you should have gotten out of today's video. But anyway, we're going to do these 3 metal specimens, and we're also going to do 2 wood specimens. An oak specimen like this, and then we've also got some birch specimens as well, and that'll just give us something to compare between for the 2 wood specimens. All right, good news here is that lab 5 is pretty similar to lab 4. So this is all the machine preparation, and I will have all the samples for you. I will have the round-faced jaw inserts in the machine, like it says here. That's what I was talking about before. For the specimens that are round, we're going to have to use the round jaw inserts. So I will have those already in the machine. And the first part that you're supposed to do here in step 4 is to measure the dimensions, but I'm not even going to ask you to do that. I'm going to give you the dimensions here. That way we don't have to waste any time in the lab. So for the metal specimens, the diameter of the test section right here, this diameter is 0.35 inches. All right, so you're going to need to get the cross-sectional area in order to calculate the stress. And remember, the cross-sectional area is equal to pi r squared. R is the radius. This is the diameter. So divide this in 2 to get the radius, then square it, then multiply it times pi to get the cross-sectional area in inches squared. The other thing you'll need for the metal specimen is the gauge length. That is the length of this test section right here. And I'm going to tell you what it is. It is 2.0 inches. So this is the original length that you will use for your strain calculations in this lab. All right, so 0.35 inches in diameter and 2 inches for the gauge length. That's for the metal specimen. For the wood specimens, the diameter here is 0.625 inches. That's 5/8 of an inch. And the gauge length, well, it's kind of hard to tell, but here's the number I want you to use. when you insert this specimen into the jaws, you're going to insert it kind of like that and like that. You should leave just a little gap. I'm simulating my hands or the jaws. So when you put the specimen in, leave a little gap, like about like that, between the bottom of the jaws and the bottom of the specimen. And if you do that, it looks like, I think my fingers are a little bit longer than the jaws. If you leave just a little gap in between the specimen and the bottom of the jaws, then what you're going to find is that the distance in between here, the test section in between the jaws, is going to be about 2.5 inches. So we're going to use that as the gauge length for the wood specimens. So for the wood specimens, diameter is 0.625 inches. Gauge length is going to be 2.5 inches. Okay, I'm telling you that so that we save some time on the day of the lab. All right, then a lot of this next stuff is pretty similar to the plastic test for lab 4. So I'm not going to go through this in huge detail. Make sure that you tighten the jaws by turning the crank in the correct direction. And just look at those arrows on the jaws. They'll tell you which direction to crank it, to tighten it. The metal specimens, you don't have to crank it super tight because the jaws dig in pretty easily to the metal specimens. With the wood specimens, what tends to happen is if you don't crank it down real tight, then what happens is the wood tends to slip out of the jaws. It tends to pull out of the jaws just like that. And then your test data will be garbage. It'll be invalid test data. So in order to make sure it doesn't slip out of the jaws, what you need to do is crank it down pretty tight for the woods. You need to make sure those jaws are clamping down real tight on the wood specimens so that the wood specimens don't slip out of the jaws as they start to try to pull it apart. All right. Read through here. I'm not going to read everything to you, so make sure you read through this before the lab day. Also, make sure you bring this to the lab. One other difference between this lab and lab 4 is the extensometer. We're going to use the extensometer for the metal specimens and only for the metal specimens. So when I gave a demonstration for that a week or two ago, but you're going to basically attach those clips to the metal specimen, right, like that. Remember, I showed that in a video a week or two ago. So you're going to attach your extensometer to the metal specimen once the metal specimen is already installed in the machine. So first go ahead and install the specimen in the jaws in the machine, get it tightened down, and then install the extensometer clips onto the test specimen of the metal specimen, okay, the test section of the metal specimen. All right, here's a note. It doesn't really matter whether the extensometer is installed right side up or upside down. All it's measuring is the separation distance of those two clips. And what I have observed anecdotally is it actually works better. The extensometer tends to stay in position better if you install it upside down so that the label, the words, Instron, are actually upside down. I'm not real sure why it works better upside down. It just tends to stay in position better and it doesn't slip as much if you install it upside down. Maybe it's because it's been used right side up more, and so maybe the little points that are supposed to bite into the material, maybe they're getting worn down in that direction and they're not as worn in the other direction. I don't know, but it tends to work a little bit better if you install the extensometer upside down. Okay, then you go to the PC and you click on the test button, and the file name, or I should say the test program, is going to be TEC 293 metals tensile testing. That's going to be one test procedure, and then you're going to have to use a different test procedure for the wood tensile testing. And the main reason they're different is because the metals tensile testing is programmed to use the extensometer, and the wood tensile testing is not. It does not use the extensometer. It just uses the movement of the moving crosshead to determine the extension of the test. Then enter your file name, enter your names of your group members, and then a brief description. That way we will know which file is yours. Once again, this is important in step 11. You need to zero out the machine. So zero out the load from the load cell on the machine by clicking on balance load. That will bring that down to 0. And also click on zero extension. That zeroes out the extension of the machine, so it starts from 0. All right, and then once again, we're going to see real-time updates of the stress-strain diagram on the computer screen, so you can follow along. It's kind of fun to follow along with the test as you see it pulling the specimen apart. And then when it detects that the specimen has failed, it's going to stop the test automatically. You need to make sure you click the Finish button. That's going to save the data to the computer. And then once again, I will, at the end of all the testing, I will move all the files onto ReggieNet so that you can access all the files on ReggieNet. And then it's going to ask you, do you want to do another test? And if you want to do another test of the same kind, as in, okay, you just did the aluminum, now you want to do the 1018 steel, then the answer is yes, because you want to do another metals test. But if you just got done with all the metals and you want to do a test of a wood, then the answer is no. You got to go back to the beginning and start with a new test procedure, the woods testing procedure. All right, so if you're doing another similar material, then click yes. If you're doing a different type of material, then click no. All right, and that's it for the test procedure. Then we get to the results on page 49. So I want you to create a stress-strain curve, just like you did in Lab 4. Create a stress-strain curve for each one of the 5 specimens. Make sure you label all the axes with units. There needs to be a title. The horizontal axis should be strain in inches per inch, and the vertical axis should be stress in PSI. We're going to use engineering stress, which just means we're going to use the data provided by the machine. On the stress-strain curve, I want you to label the point where the yield strength is reached. So you can just label it sigma sub y if you want, or you can write in yield strength if you want. That's fine too. I also want you to label the ultimate tensile strength. You can label it sigma sub u, or you can write in ultimate tensile strength. That's fine too. And I also want you to label where it failed. So you can write in failure on the plot, or you can write in sigma sum f for stress at failure. And then, like before, make sure under the plot you label it with a figure number, and then a brief description, like stress-strain curve for 1018 steel, or something like that. All right, then for the calculations in tables for your results, I want you to calculate the elastic modulus, E, for each of the materials. Remember, that's just the slope of the stress-strain curve. So pick 2 points on the linear portion of your stress-strain curve, and then calculate the slope in between them. Rise over run. Make a table and show your results in a table. Show your calculations, how you did that, how you did the calculations. Then I want you to make a table showing the yield stress and the ultimate tensile strength for each one of the materials. And I want you to calculate the maximum elongation in percent when it failed. So in other words, what was the elongation in percent when the material failed? And here is a calculation that you can use to calculate that. The final length is the length when it failed, and the original length is the gauge length. So the final length is going to be the change in length for the extension plus the gauge length. All right. And then divide by the original length and multiply by 100 to get the percent elongation. The discussion questions are pretty similar to the ones for Lab 4. First, I want you to write a good paragraph or 2 comparing and contrasting the properties of each of the materials. I want you to answer these, and I want you to explain how you know. Don't just answer them. I want you to explain how you know what the answer is. I want you to tell me which had the highest elastic modulus, which had the lowest, which had the highest yield strength, which had the lowest, which had the highest ultimate tensile strength, which had the lowest, which was the most brittle, which was the most ductile, which was the toughest, and which was the least tough. All right, note that all of these except these last two, tough and least tough, you can do with calculations. These last two regarding toughest and least tough, I don't expect you to do those calculations because remember, this is the area under the stress strain curve. And to do that, you have to do some more advanced manipulation of the data set. And I don't expect you to do that. Just look at all the stress strain curves. Note the axes, right? Because the axes might be different for these different materials. So note the axes and tell me which one you think has the highest area under the stress strain curve. That's going to be the toughest. And which one has the lowest area under the stress strain curve. That's going to be the least tough. The last three questions are just applications. Let's say you're building a car frame, a chassis of a car. Then which of the materials that we did in this lab, which of those materials would you like to use? Explain why. Second application question is an airplane frame. So if you're going to build one of these, which of the materials in this lab would you like to choose? Explain why. And the last one, if you're going to build a tree house and you're going to build it out of wood, so which wood that we tested in lab 5 would you like to use to build a structural component for the tree house? All right, so which of the two woods would you like to use to build a structural component for the tree house, and explain why? All right, so that's the explanation of Lab 5. Make sure that you have read through it before coming to the lab, and make sure that you bring your safety glasses and your mask and your lab manual with the instructions. All right. Once again, my role in the lab is to answer questions, so I will answer questions that you have in the lab, but mainly I'm there as a safety observer. I want to make sure that nobody seriously injures themselves. So I'm not going to step you through the procedure step by step. You're going to use this video and your understanding of the procedure as well as the lab manual. You should be following along in the lab manual step by step. And I will tell you if you need to do something differently. All right, but make sure you have your lab manual and your safety goggles, glasses, and your face mask. All right, so that's going to be it for today's videos. Let me know if you have any questions about any of the materials that we covered today. Otherwise, I look forward to seeing you all in Lab 5. I look forward to destroying some metal and some wood specimens. So I'll see you in the lab.